Hello everyone, welcome to another video tutorial. Let's continue solving the problems of the chapter 3, problem 4. Before starting to solve this problem, let me show these typo errors that we had in the reference in the chapter 3. Yes, we discussed these equations, and here was one typo error that we had. This equation, okay, the summation of the co-energy and energy, okay. So I found the second edition. This is the file, the second edition of the reference. Here you can see the correct equations in this version. If I find right this important equation for summation of the co-energy and energy, we had two equations. One of them was for force calculation, one typo error, and one was for summation of the energy and co-energy. Okay, so here is the summation of the energy and co-energy. This equation, this is the correct one in the second edition. And also here you can see the right typo error here. We had another equation for calculation of the force using the energy function. Okay, we should have a negative sign here. So in the second edition, you can see the correct equation. Okay, so yes. And also let me explain this equation that we used for calculation of the force. One guy asked me about this equation, the derivation procedure, why we discussed this assumption when we neglected the reluctance and we derived this equation for the force. So how to answer this question, how to derive this equation for calculation of the force? You know, here in this structure, for example, this is a good question. You know, this is a good question, and you can answer to this question using several methods. We have several ways to derive this important equation. So in this case, for this magnetic structure, let's consider these two positions. I am going to use extreme values. So suppose this is the air gap 1, 5 millimeters. So let's take an image. And also suppose we have another position, for example 1. Copy image and paste it again. So we have these two cases. So let's use the energy method for calculation of the force. You know that using the energy method, the force is equal to negative of partial derivative of the energy with respect to x when the flux linkage is constant. The flux linkage is constant. So here in this problem, when you consider this flux line in the middle of this structure, okay, so how much of the length of this flux line is inside the iron and how much of it is inside the air gap? You remember the length of the core was equal to 60 centimeters. Yes, this is the length of the core. 60 centimeters. The length of the air gap is in order of millimeters, right? 1 millimeter, 2, and so on. So the length of the air gap is much lower than the length of the flux line in the core. This is one important point. Keep it in mind. And how we can calculate the energy? The energy is summation of the energy in the core plus summation of the energy in the air gaps that we can have. Okay, so here we have one air gap. So this is the energy in these two cores that we have, or energy stored in the iron part plus the energy stored in the air gap. So when we take the partial derivative for calculation of the force, we have these two derivatives. Derivative of the energy in the core with respect to x minus derivative of the energy in the air gap, right, with respect to x. So when the flux linkage is constant, what is the value of the flux linkage? The flux linkage is n number of turns times phi times area. Okay, so when the flux linkage is constant, because the number of turns is constant for both situations, the area. So in this case, the value of the flux must be constant. Okay, the flux for these two cases when we change the air gap. And consequently, the flux density in the core is constant, B. So here, when we move this object, we don't have a big change in the length of the flux line inside the core. So the variation in the value of the energy in the core, stored energy in the core with respect to x, right, is close to zero. The variation here. And the variation of the energy in the structure is associated with the variation of the energy in the air gap. Okay, so this is the point. This is the point. And we know that the energy in the air gap is B gap to the power 2 divided by 2 times mu 0, the cross-sectional area times gap. When you take the partial derivative with respect to the position coordinate, we will have this equation. This is the value of the force. Okay, did you get the point? You should review this procedure for calculation of the force. How the energy changes in the iron part and in the air gap. When we have a small variation in the air gap length and keep the flux linkage constant, the energy change is associated with the energy change in the air gap. So let's do an experiment in the ANSYS Maxwell software. I want to use this equation, negative of partial derivative of the energy with respect to x position. Suppose we have this table. I am going to change the value of the gap 1 millimeter to 1.1. Suppose we have 0.1 millimeter displacement for the moving object. And I am going to keep the value of the flux linkage constant. So in this case, we should modify the value of the current we should modify the value of the current if we are going to keep the flux linkage constant, and calculate the energy stored in the iron parts and energy stored in the air gap to calculate the force. So here also we have this F. Let's fill this table, then we can discuss details. This is Fx. This is the first case. Problem 3, set the air gap equal to 1, and this is the value of the current, the default one. So how to calculate the energy stored in the iron parts and in the air gap? Let me define this rectangle here, right, to calculate the energy in the air gap. Rectangle 6, the position is this one, x size is gap, y size is 5 centimeters or 50 millimeters, this one. This is the air gap. And I can calculate the stored energy, calculator, stored energy for the iron parts. Here, this is the total energy we calculated. So let's select the energy, and here from the geometry I should select iron parts. So this is the iron part 1, iron part 1, and this is the iron part 2. This is the air gap. Okay, so in calculator we should use this. This is the energy, and geometry, surface, iron 1, calculate the integral. Again, select the energy. Iron part 2, calculate the integral. Excuse me, the quantity, energy, surface object. Calculate integral. Integral of surface, right? Iron 1, energy. Finally, summation of these two terms. This is the energy stored in the iron parts, in the core. And how much is the energy stored in the air gap? Here, surfaces, air gap, calculate this integral. So this is the energy stored in the air gap. We segregated these two terms. Perfect software. And now let's analyze the structure. Analyze to calculate the flux linkage, the stored energy in the iron parts and in the air gap. So data table, force, let me multiply this by, you know that, 5 centimeters divided by 1 meter to have, right, the correct value. This is the value of the force. The flux linkage is this one. This is the value of the flux linkage, 0.69 Weber. And here, from the field reports, we can plot the core energy and the energy in the air gap, stored energy in the air gap. So the stored energy in the air gap is much higher than this one. So let's increase the field precision 4 and 4 points here. So we have these numbers now. The air gap is 1, the coil current is 0.93, the coil current. is 0.93, the value of the force Fx is equal to minus 249 249.4 Newton, and the value of the flux linkage is 0.69. 0.69. The stored the stored energy in the iron parts is 0.0403, 0.0403, and the stored energy in the air gap is 0.2476. Okay, this is the stored energy in the air gap. Now let's change the position 1.1. In this case, if I repeat the analyze, then we can check the numbers, the calculated force. Okay, so here is the value of the force, and here you can see the change in the value of the energy. But in this case, the value of the flux linkage is 0.64. The value of flux linkage must be 0.69, okay, because we are going to use this equation. The flux linkage constant. So we have to increase the value of the coil current. So let me increase it to 1. Repeat the analysis to check the number. We should adjust the value of the current. Here is 0.68. And if I write 101, repeat the simulation again, we can match the number 0.69. So here is the value of the the value of the flux linkage is the same as the previous one. The value of the current is 101 in this case. The value of the flux linkage is 0.69. What is the value of the force? The value of the force is close to the previous one, minus 249.7, close to the previous one. Now let's check the value of the stored energy in the core. 0.0409, 0.0409. The value of the energy in the gap 0.2723, 2723. So as you can see here, variation of the energy in iron parts is very low, right? The partial derivative is 0. And if we approximate this by delta WFG, change in the energy of the air gap, divided by delta X, so let's calculate this. This is equal to 0.1 millimeter, the change in the value of the air gap, and the difference between these two numbers. So we have this 20.2723 minus 24.76 divided by 0.1 millimeter. So we should change this to meter times 1e minus 3, 247, right? Close to this number. We approximated this equation by this equation, and we calculated the force. So this is why this equation is really good for calculation of the force in these structures, right? And when we have air gaps, you know the reason the length of the air gap is much lower than the length of the flux in the core. We have a uniform flux density in the air gap. Considering those assumptions, we derive this equation. Again, you can review the procedure explained in the reference, and also you can repeat this experiment. Okay, we have this great software. We can do this kind of calculations, right, to evaluate the formulations presented in the reference. Anyway, a good point, a good right simulation. You can repeat that. Let's go for the next problem. Figure P 3.4 shows an electromagnet system for lifting a section of a steel channel. The coil has 600 turns. The reluctance of the magnetic material can be neglected up to a flux density of 1.4 Tesla. A, for a coil current of 15 amps DC, determine the maximum air gap for which the flux density is 1.4 Tesla. Okay, the part A. Here is the structure of the problem. Yes, the electromagnet system. So let me copy this. Here we have this steel channel, this one, and we have this coil. Yes, the number of turns is 600. By exciting this coil, we have a force in the y direction applied to this steel channel. According to this problem, when the flux density is below 1.4 Tesla, we can neglect the reluctance of the iron. So in this case, if we want to have 1.4 Tesla in the air gap, what will be the value of the gap thickness? So simply you can write this equation. If I consider this flux line, here is the direction of the current, the DC current. If I consider this flux line, okay, this one or this one, here as you can see, the thickness of this limb is 8 centimeters. That is the same as this one. And the thickness of this part in the middle is the same as the summation of these two. So we should have the same flux densities in the air gaps, right? 1.4 Tesla. So for this flux line, you can write integral of h dot dl equal to ni. We have, right, this integral of h dot dl for the iron part, dl for the iron part for the core, plus we have one air gap here in front of this flux line. If you follow this flux line, and we have one air gap here. Okay, so this is 2 times h gap times the gap thickness is equal to ni. This part is 0 because we neglected the magnetomotive force drop in iron. Iron is ideal, so we can write this equation. The equation that we have here, ni is h gap the magnetic field intensity in the air gap times 2 times the air gap thickness. Yes, we have two air gaps in front of this flux line. Yes, this is important. Depending on a structure, you should detect, right, the correct number. Anyway, so here, instead of h gap, we can write b gap divided by mu 0. And finally, the gap thickness will be equal to mu 0 and I divided by 2 times b gap. If you replace the numbers, okay, for the mu 0, the number of turns 600, the value of the current 15 amps, 2 times the b gap 1.4 Tesla. The air gap thickness will be equal to 4.04 millimeters. So this is the part A. Let's simulate also this problem in the ANSYS Maxwell software. Investigate calculations. So let's save as this problem 4 and delete this one. I'm going to generate a new design. How we can generate this model in ANSYS Maxwell? It is not too complex to generate this model in the software. We have this structure, we have these two air gaps, okay, and here, one air gap here. This is the steel channel and this is the stationary part. So let me generate this rectangle first and set the width and height of this rectangle. I am going to consider half of this structure, okay, to generate the model. Then we can duplicate mirror and generate the full structure. So 16 divided by 2 plus 8 is 16. So here the x size 16 centimeters, the y size, here you can see the y size, okay, is 8 plus 40 plus 8. Also we have this gap, we define a parameter for that. So 40 plus 8 plus 8, that is 56 plus gap. So here I write 56 centimeters plus gap 1 millimeter. Okay, so we will check that. So this part of the structure, and now we can subtract this part inside the object that we created. We didn't consider this length yet, right? This dimension is not given in the problem. Yes, is not given here. So I'm going to consider it equal to 10. Okay, or let's define a parameter for that. We should add up it here, 16 centimeters plus the width. Let's consider 10, this one. So now we can draw this rectangle. This is the 8 x size, the y size is 8 centimeters, the width is w, the height is 40 centimeters, this one. So select this one and subtract. Now we should create these two air gaps. Okay, we have one air gap here and one air gap here. So this rectangle, let's set the dimensions 0, 8 centimeters, and 0, the x size is 8, the y size is gap. Let's increase the value of the gap to 5. Yes. And this one, the position is 8 plus width. This is 48. Okay. And 0. Again, x size is 8. Y size is gap. You can imagine that just I created these two air gaps. Okay. So we have one air gap here and one air gap here. This is the first rectangle that we created. This is the rectangle that we subtracted. The y size is plus gap here, 40 centimeters plus the gap. Now I can select this one, these two air gaps, subtract. Yes, the structure we created. So select this object, and from here, edit, Boolean, separate bodies. We have two objects. We can select both, duplicate mirror, select the origin, and a point on x-axis. Okay, so this one, unite, these two unite. We created the structure of the problem. Okay, perfect. Now let's create the coil arms. We have one coil arm here. So for this rectangle, let's set this position equal to 8.2. For the x size, the y size, again the same. This is equal to w divided by 2, and the same. This coil, so yes, then we can duplicate and mirror it with respect to the x-axis. So select these two objects. Copper material we should select, and in this case we should assign ideal iron to these two parts, this part and this part. Assign material, let's select the iron and increase its permeability. So the iron material that we used also in our previous problems. Here is the iron material that we added. Let's consider 100,000 for the magnetic permeability. Consider it ideal. Now let's define the excitations. For this problem, we have two coil arms according to this. For this coil arm zone, the direction of the current is into the paper, and for this part is out of the paper. You know that we simulated these structures multiple times. 600 is the number of turns. So for this, assign excitation, the total current, negative 600 times coil current. Coil current is 15 amps. Okay, for this excitation. And for this one, assign excitation is out of the paper. Into the paper, out of the paper, we assign the ideal iron. So now we should draw the region, assign the boundary conditions. So draw the region 100% offset, select edges, selection mode edges, select these four edges, zero vector potential boundary condition. That's all. Now we can add solution setup and solve the problem. Also, let me select these objects to assign a good mesh 1 centimeter inside them and analyze. Repeat the problem, right? The solver. So now we can plot the flux density B. How much is the value of the flux density in air gap? The range here is high. If I consider 1.4 Tesla, yes, we have 1.4 Tesla for these regions. Also, we should plot, right, the exact value of the By that we have. So let's plot flux lines inside the structure. That is actually a good visualization in this case. Flux lines. So how we can plot the magnitude of the B in air gap? You know that. Let's delete B and A. I'm going to add a right line object in the middle of the air gap here. So this is negative 8 centimeter. The y is 8 plus gap divided by 2. The second point, the x just is 8. This is in the middle of the air gap. Let's analyze the structure again to check the level of the flux density in the air gap. So polyline 1, magnitude of the B. What is the value here? Let's assign X marker is 1.2 Tesla. Because in this case we have this value for the air gap. We didn't set the correct value. The value that we calculated is 4.04. So here 4.04. The value of the current is 15 amps. So let's repeat the analysis. Then we can check the level of the flux density in air gap for this ideal iron. 1.4. Let's calculate the average value. 1.43, 1.4. So correct. We simulated the problem using the ANSYS Maxwell software. Let's hide the enclosure and just focus on the structure. When the value of the current is 15 amps and the value of the air gap is 4.04, the value of the flux density is 1.4 in the air gap. We calculated it considering this integral, neglecting the magnetomotive force drop in the iron. So you can redo the simulation and investigate this equation. So part B, for the air gap in the part A, determine the force on the steel channel. How much force F in the y direction is applied on this steel channel? The depth of the problem is given here, 80 centimeters. So we can calculate the cross-sectional area of these 3 air gaps. Yes, we have 3 air gaps. We have one component of the force here, one component of the force here, and another one here. So if we use this equation again, B gap to the power 2 divided by 2 times mu 0 times the area of the gap, we can replace these numbers. The value of the flux density in the part A was equal to 1.4 Tesla to the power 2 divided by mu 0 times AT, right, is the depth of the problem. This is AT, the depth. So 8, this one, plus 16 plus 8, the total width times 80, the depth of the problem, times 10 to the power minus 4, because these are in centimeters. This will be the value of the force. Let me recalculate it again in MATLAB. So 1.4 to the power 2 divided by 2 times 4 times pi times 1e minus 7, the mu 0 times the 8 plus 16 plus 8 times 80 times 1e minus 4. Okay, the contact area. The gap, area of the gap is the contact area between this part and this stationary part. We have these 3 air gaps. So, yes, the value of the force is 199 kilonewton. I calculated the force correct, just a typo error we had here. So now let's calculate the force. In this case, assign parameters force to calculate the force on this object. Perfect software. Yes, how ANSYS Maxwell calculate force using energy or co-energy method or advanced methods, Maxwell stress tensor. Okay, so let's clean up the solutions and analyze the structure again. I am going to calculate the force using ANSYS Maxwell and compare. So magnetostatic report, data table, the Fx and Fy. So we should multiply by the depth of the problem. 1 meter. So this is Fx. The value is very low, right? And this is Fy at 205 kilonewton, right? Why the value of the Fx is very low? Because we have a symmetric structure, right? The value of the force in the x direction is 0. We have a symmetric structure with respect to the y-axis. But the value of the force in the y direction is 205 kilonewton. We approximated this number, 200 kilonewton, rough calculations. So this is the exact calculation using the finite element software, considering flux, right, leakage, the leakage fluxes that we have, fringing effects, and so on. But still, our approximation works good. Okay, we approximated this number with a good precision. Part C, the steel channel has a mass of 1000 kilograms. For a coil current of 15 amps, determine the largest gap at which the steel channel can be lifted magnetically against the force of the gravity. What is the value of the force of the gravity? Is mass times acceleration. Yes, the force of the gravity is mass times the acceleration. The mass is given in the problem 1000 kilograms. The acceleration of the gravity is 9.81. So we are going to calculate the maximum air gap thickness that can generate this force, this one here. So we can derive this equation here. This ratio between forces for these two cases. The value of the current, right, is the same for this case and the previous case. So the value of the force, the magnetic force, is equal to B gap to the power 2 divided by 2 times mu 0 times the area of the gap. This is constant. These two are constant. So Fm is proportional to B gap to the power 2. B gap is mu times H gap, mu 0 times H gap, that is equal to mu 0. H gap is Ni divided by 2 times the gap thickness. So the force is proportional to the current to the power 2. Also is proportional to 1 divided by the gap to the power 2, right? According to this equation. This one. So you can write finally the magnetic force for the case 1, right? This fraction, the magnetic force for the case 2, when we change the air gap thickness divided by the magnetic force for the case 1 is equal to gap 1 divided by gap 2 to the power 2. Consider that for derivation of this equation, we assumed that the current is constant for both cases. Here 15 amps and 15 amps here. The value of the coil current, right, is the same for both cases. So yes, what is the value of the force for the second case? For the first case, we calculated this force. For the second case, we are going to compensate this force of gravity. The force of the gravity, we can calculate it using this product. So this is the air gap thickness 1. Finally, this will be the air gap thickness for the second case, 18.2. So what is the value of the force here? 9.81 kilonewton. Yes, for the second case. This is 9.8 kilonewton. If we are going to lift up this steel channel with this mass, 1000 kilograms, we should apply this force. The maximum air gap thickness that is possible to generate this force is this one, 18.2 millimeters. Let's test in the software. 18.2, the new air gap thickness. In this case, because we have a higher air gap thickness, we have fringing effect. So let's rerun the simulation and compare the numbers. Can this structure generate 9.8 kilonewton or not? For this case, the value of the force in the y direction is 11.3. We wanted to have 9.8 using the manual calculations and this approximation. So this works good. Okay, so as you can see, in this case, the force is above 9.8 kilonewton, and for this air gap thickness, we can lift up this steel channel. Okay, good. So you can redo the calculations, generate the ANSYS Maxwell model, and try this problem. Let's go for the next problem. Problem 5. An electromagnet lift system is shown in figure 3.5. This one. The coil has 2500 turns. The flux density in the air gap is 1.25 Tesla. Again, assume that the core material is ideal. A. For an air gap thickness equal to 10 millimeters, determine the coil current, determine the energy stored in the magnetic system, determine the force on the load, the sheet of steel, this is the load, determine the mass of the load. Acceleration due to the gravity also is given here. So this is the structure of the new problem. Again, we have this coil. This is the direction of the coil current. Yes, the direction of the coil current that we have. The direction of the field generated by this coil is in this direction. You can plot this flux line here and this flux line here. We have 3 air gaps for this problem. So how we can calculate the value of the coil current when the value of the flux density is given and the value of the gap is given? Again, we can write this equation. Integral of h dot dl is equal to ni. If you consider this flux line, we have 2 air gaps in front of this flux line. The magnetomotive force drop in iron is 0 because we have ideal core material. So we can write h gap times 2 times gap thickness equal to ni. This is b gap divided by mu 0 times 2 times gap is equal to ni. So what is the value of the current? Is b gap times 2 times gap divided by mu 0 n. You can replace the numbers. The value of the coil current will be 7.95 amps. Yes, the value of the coil current in this case. Let's check the numbers here for the chapter 3. 7.95. The value of the current for the part A, right? The first part of the part A. Determine the energy stored in the magnetic system. Because the core material is ideal, the energy stored in the system is only equal to the energy stored in these 3 air gaps that we have. So the energy stored is equal to the energy stored in the gap, that is equal to B gap to the power 2 divided by 2 times mu 0, the energy density. Yes, this is the energy density in the air gap times the volume of the air gap. If you replace the numbers, how much is the volume of the air gap? Is the total width 20 plus 40 plus 20 times the depth of the problem is 10, is 40 times the air gap thickness, that is 10, is given here. We are going to calculate the total volume for these 3 air gaps times 10 to the power minus 9, because all of these numbers are in millimeters. We should change them to meter. The value of the energy, stored energy in the magnetic system, is 19.8 joule. You can investigate this number. And the next part, determine the force on the channel right, on the load. How we can calculate the force? Again, we can use this equation, B gap to the power 2 divided by 2 times mu0 times the area. We have three air gaps, three cross-sectional areas. The summation of these widths plus this one, times the depth of the problem, times 10 to the power minus 6. These are in millimeters. The value of the force is equal to 1980 Newton. We have the same number here. The next part, determine the mass of the load. Yes, when we apply this force, this electromagnetic force, that is equal to the force of gravity, mass times acceleration. Yes, so we can lift this load. In this case, we have the acceleration. We calculated the force, the electromagnetic force. The mass will be equal to 201 kilograms. Yes, 201 kilograms, the number that we have here. So, the next part, part B, if the air gap is 2 millimeter, determine the coil current required to lift the load. In the previous case, the air gap thickness was 10 millimeters. And if we change the thickness of the air gap, how much current is required to lift this load? We should have a lower current, right? Because in this case, the air gap is high. And to generate flux density in the air gap, we have to impress more current to the coil. In the case that we have a lower air gap, yes, using a lower value of the current, we can build up the required flux density in the air gap. So this is the equation, right? In this equation, the value of the air gap flux density is important for equation of the force. And when we change the air gap thickness to have the same amount of the force, we should change the current to build up the same flux density in the air gap, right? This is the point of the problem. For this case, again, we have this equation. The force is proportional to B gap to the power 2 is proportional to this expression, this one, and in this case, because we change the value of the current, we should consider both current and gap thickness, unlike the previous case. In the previous problem, the value of the current, right, was the same for both cases. In this case, we change the value of both current and air gap. Okay, so we have this equation in general. The force for the second case divided by the force for the first case is I2 divided by I1 to the power 2 times gap 1 divided by gap 2 to the power 2. We are going to have the same force, right? According to this one, we are going to lift the same load. The force of the gravity is the same. In this case, Fm2 is equal to Fm1. So this fraction is 1. And the value of the I2 is I1 times gap 2 divided by gap 1. If you replace the numbers, I1, this is the I1, 7.95 times the new air gap thickness, 2 divided by 10. That is equal to 1.59. So a much lower value for the current. So as you can see, for the same value of the force, when we reduce the air gap linearly, the value of the current also will decrease linearly. What is the number here? 3.97, different from the number that we have. I checked the second edition. In the second edition, if you check this problem, this is the case. If the air gap is 5, so again we have a typo error here, 2, because if we multiply 7.95 times 5 divided by 10, we will get this number, 3.97. So this number is correct, 5. This should be 5. If this is 2, so this is the correct number. If this is the 5, this is the number that you have here. Anyway, okay, so now let's go for the next problem. Problem 6. The cross-section of a cylindrical magnetic actuator is shown in this figure P3.6. The plunger has a cross-sectional area of 0.0016 meter square. The coil has 2500 turns. We have this coil. This is the plunger, the stationary part, and this is the moving part. We have this gap here, this air gap. The resistance of the coil is 10 ohms and a voltage of 15 volts DC is applied to the coil terminals. Assume that the magnetic material is ideal. A. Determine the air gap in millimeter for which the flux density in the air gap is 1.5 Tesla. Determine the stored energy for this condition. Yes, again, we have ideal iron core. So let's plot the flux line. Here we have one air gap. And here we have two contacts, but the thickness of the air gap is very low for this location and this location. We can neglect the magnetomotive force drop on them. So if we consider this direction for the current out of the paper, this will be the flux line in this case. So here again we can write this equation, integral of h dot dl equal to ni. Okay, so as you can see, only we have one air gap in front of this flux line. So h gap times gap is equal to ni. The equation that we have here, again, instead of h gap, we can write b gap divided by mu 0 times gap, and the air gap thickness will be equal to mu 0 ni divided by b gap. If you replace the numbers, the thickness of the air gap will be equal to 3.14. Yes, this is the part A. And also we should determine the stored energy for this situation. The stored energy is equal to the stored energy in the air gap because the iron is ideal. B gap to the power 2 divided by 2 times mu 0 times the volume of the gap. We have the cross-section area of the gap times the thickness of the air gap. Okay, so this is in meter square, this is in millimeter. The value of the stored energy will be equal to 4.5. Also, you can simulate this structure in the ANSYS Maxwell software. Okay, so we have a cylindrical magnetic actuator. Let me save as this project problem 6 and delete this design. So we can add a new 2D Maxwell design. We have cylindrical symmetry in this case. Okay. So we can generate the geometry considering this solution type. The solution type is in the cylindrical about z coordinate system. So x and z. How we can generate the geometry of the plunger? Here I can generate this rectangle first. Okay. The cross section area of the air gap is 0.016 meter square. So we know that the cross sectional area is a circle. Okay. What is the area of the circle? Is pi times r to the power 2. The area of the circle, this is the radius, 0.0016. So the value of the r, if we consider millimeter, the unit millimeter, the value of the r is equal to sqrt of 0.0016 times 1e6. To have it in millimeter, square divided by pi. So this is the radius, 22, okay, 0.6. This is r. Pi times r to the power 2 times 1e minus 6 is the area. So here in the ANSYS Maxwell, I set this x size in millimeter. The y size, let's consider 100. The position of the corner point, let's consider this position. So this will be the cross section of the moving part of the plunger, the cross section. For the stationary part, we can draw this. You can consider exact coordinates. Okay. So let me consider this, for example. Okay. Just arbitrary dimensions. Here I'm going to consider. So we can draw this according to what we have in the figure of the problem. Finally, let's close this polyline. This is the stationary part. So let's set the dimensions. For this polyline, the first point I use, let's define this parameter, the radius of the moving part, rm. This is the radius, and this is the size dimensions that we can consider for the coil or other dimensions that we have. So for this rectangle, also let's define this. This is the radius of the moving part. Okay, so these are the same. This one, the position, the z, I'm going to consider it equal to 0. Here, okay, because I considered this size, this y size equal to 100. For this edge, this one, the second point, I should consider 100 millimeters. Okay, this contact. Then we have this line. Again, this is 100. This is the radius of the moving part. Radius of the moving part. Again, we have this radius of moving part for the first coordinate of this point, just geometry. And here for this segment, The final one, this is the radius of the moving part. Also, you can fix dimensions. I mean, if you want to have the same thickness, okay, for all dimensions, the same thickness here, not important. Just I'm going to visualize the case. I can select this, move it in this direction. Here we define this parameter, the gap that is equal to, let's say, 5 millimeters. The air gap thickness 5 mm. Now we can control. For example, 10, 0. Yes, we can determine the size of the air gap. However, we have also this contact with 0 air gap thickness. You know that. So we can generate this for the geometry of the coil. So let's change the color, the coil geometry, and the material of these two objects, ideal iron. This is copper. Okay. So let's save. This is a 2D cross section. But if we want to create the 3D model, from here, create 3D design, angle of sweep 360, full sweep. We generated this geometry for the plunger. So let's change the transparency of this object. We are going to see inside of this. Now you can visualize the geometry of the coil, and this is the moving object. If I change the value of the gap thickness to 20, okay, so you can realize how movement occurs for this plunger system. Gap equal to 5. Okay, so let's hide this object. This is the cross section area. Face selection. Okay, measure the object. The area is the same as what we have here, this number. This is the cross section area of the air gap between the moving part and this stationary part. So this is 2D view, two-dimensional view. And if I calculate if I set the air gap equal to this one and calculate the energy, can we get this number or not? Let's try. In this case, let's draw this region. Okay. Change the transparency to 0.9 and select this edge, vector potential, the boundary condition equal to 0. Okay. The vector potential equal to 0, and here we should select this copper, assign excitation. The number of turns is 2500 times the value of the coil current is equal to 1.5. Yes, the DC voltage is given here, the resistance of the coil is given here, V divided by R. This is the value of the current, 1.5 amps. The direction of the current, positive. That's all. So we define boundary conditions, excitation. Now we can define the solver. So let's analyze. Then we can visualize the flux density and flux lines. So let's select all objects except the enclosure. I don't want to select the enclosure. Fields, plot magnitude of the B. So here the magnitude is 1.5 Tesla. Let's set the scale to 1.5. Okay, as you can see here, In air gap we have 1.5 Tesla, and you can select all objects again to plot blocks, lines. Yes, due to symmetry, you don't need to, yes, generate this part. This part is calculated by the ANSYS Maxwell. We have symmetry in cylindrical coordinate system, even when you generate the B plot, the flux density plot. You can consider that. Okay. So if I select these three objects, B, magnitude of the B, you can select the full model. Okay. So we have this case. Again, let's set the scale. This is the solution of this problem. We have this fringing effect. Also, you can plot the Z component of B in the middle of the air gap. The thickness 3.114. Save. How we can calculate energy from Maxwell to the fields calculator? We can calculate the total energy for all surface objects. For all objects, the total energy, also the energy is stored in the iron parts and air, right? But in the problem, only we calculated the energy in the air gap. We neglected energy in other locations. Let's compare. Calculate the integral of this expression. Where is the integral? Integral in xy or rz? We are going to calculate integral in the rz plane. So total energy in the field. Let's repeat the simulation to check the numbers. From field data table, this is the energy. What is the value? Equal to 6.11. So let me clean up the previous solutions and analyze the structure again. So in this case, we have a stored energy. Also here, we have fringing effect, a stored energy in this part. What if I calculate the stored energy also only in air gap? So here, let's add a new object. This one, rectangle 4, and calculate the energy for this rectangle in air gap. So again, in the calculator, we can add energy, geometry, rectangle 4. This is the energy in the gap. Calculate the integral. Okay. So this is the energy in the gap. So clean up the previous solutions and analyze. We can compare the numbers now. WFG at trace. As you can see, the number here is 4.5 joule. We didn't multiply this by the depth of the problem because we don't have a 2D problem, a cross section. This is cylindrical one, and integration is done in the cylindrical coordinate system, and this number is the correct one. You don't have the L stack like before. Okay, so as you can see here, the stored energy in the gap is 4.5, the same number that we calculated here, but we have this energy for all objects. The leakage fluxes energy is stored right in other parts. So you can now realize the differences in analytic formulations and in the exact calculations that we have using the finite element method. In the 3D case, you can repeat the same problem, calculate the field. Like before, you can define a cross section for the coil for this copper. Let me generate a cross section for it. Here we have right, you can take x z plane, okay, not important. So this copper object, edit, surface section xz, we have these two cross sections, and again edit, boolean, separate bodies, we can delete one of them. Assign current excitation for this one, current 600 times 1.5 amps. Okay, so in this case we can run the simulation. This is copper, iron, we need to add the enclosure, okay, to solve this problem. From here, draw region, consider 50% offset. So we can now run this simulation. In 3D, we don't need to apply boundary condition. All boundary condition by default is applied. So let's analyze the problem. In the 3D case, we can calculate the flux density levels. Also, we can visualize the flux lines. So let's check. In this case, excuse me, I didn't set the correct air gap thickness. So let's clean up the solutions and run the simulation again. The correct air gap thickness is 3.14. Now you can visualize the geometry. Yes, this is the geometry of this problem. And you know what is this area? The contact area between the moving and stationary part. Also, we neglected this contact. This is zero contact. The solution completed. You can select all objects, field B vectors. Yes, visualize the B vectors. This is not right a good plot. Let's select one plane, for example, the XZ plane, and plot the B vectors, streamlines here. So this is a better visualization. We did a 3D simulation and you can see streamlines of B for this case. Okay. Also, you can calculate the values that we have for the air gap, the correct value that we have for the air gap. Maybe you can reduce the mesh size, check the numbers again. Anyway, so the next part, obtain an expression for the force on the plunger as a function of the air gap length. We know that the force is equal to B gap to the power 2 divided by 2 times mu 0 times the cross section area. Okay, the cross section area that we have. So this is the cross section area. B gap to the power 2 is equal to, excuse me, instead of B gap, we can write this one. We can write this is mu 0 times H gap to the power 2. Okay? Instead of B gap, we can write this. So this is the area 2 times mu 0, and this is the mu 0 times Ni divided by gap to the power 2. So let's calculate this part and check this number that we have here. So this is 0.0016 times the value of the mu 0 is 4 times pi times 1e minus 7, and this is the value of the force, the coefficient of the force. We know that We have a coefficient here divided by the gap to the power 2. This is mu 0 to the power 2. We have 1 mu 0 here. So actually we have this value. This is times mu 0 times ni to the power 2, 600 times 1.5 to the power 2. Okay. This part divided by 2 finally. So this is the number. Why we have this number? Excuse me. I have set the number of turns wrong. So here the number of turns is correct for 2D simulation, but for the 3D simulation, this is the correct number of turns. Again, you can repeat the simulation for 3D analysis. Here in MATLAB, I have set this number wrong. Yes, 0.0141. This number that we have here. So we have found a relationship for the force. Consider that the current is constant for different values of the air gap thickness. Yes, this is the equation that we derived. And here is the value of the B. Let's set the scale to 1.5. Yes, we have this flux density level in the air gap. You can visualize these streamlines in your case. Okay, so this is the relationship, the part B. As you can see, the force is proportional to 1 divided by gap to the power 2. We derived this equation multiple times in the previous problems. And now let's solve the part C of the problem 6. Determine the force on the plunger for the condition of part A. How much is the value of the force? Here, as you can see, we have this equation. We derived this equation. In this equation, just we need to set the value of the gap thickness equal to 3.14. If you replace this number for the gap, this will be the value of the force, 1432 Newton. The value of the force. Let's check it here for this 2D analysis. If I select this object, we can assign parameters force. So again, let's clean up the solutions, calculate the force for this object. Build report data table. No, the magnetostatic report. Force along the Z axis. That is equal to 1.5 kilo Newton. Right? Close to this number, 1.5 kilo Newton. Considering all effects, we considered several assumptions in derivation, right? Neglecting the leakage fluxes, those concepts. So, yes, the closed number that we calculated here, this is the value of the force along the Z axis, the Z that we have. We didn't multiply this by the stack length anything, cylindrical coordinate system, you know that. So what about the 3D model? We can select the moving part, assign parameters, force. Here we have this option, virtual work, right? Energy and co-energy methods or Lorentz force. Let's select this one, calculate force using the virtual work method. In 3D simulation, we can select the options. So let's clean up the solutions and analyze the structure again to calculate the value of the force applied on the moving part. From the magnetostatic report, data table, we can check the value of the force for the moving part, the force along the z axis, 1.57 kilonewton, right? Again, a closed simulation. Perfect software. And as you can see, using manual calculations also we can predict these numbers, right? In the ANSYS Maxwell, using finite element calculations, we solve the problem, right? Solving the Maxwell equations. But using manual calculations, also we can predict these numbers with a good precision. Anyway, you can repeat the simulation. Part D. Suppose the plunger moves quickly from an initial position gap 5 millimeter to fully closed position. So suppose the air gap thickness is 1. The first case, excuse me, is 5 millimeter. This is the condition 1. In the condition 2, the air gap thickness is 0. So we have a quick movement. The plunger moves so quickly that the flux linkage of the coil and hence the flux density in the air gap hardly changes during the motion. So we have a quick motion. The flux is constant. Determine the force during the motion. Determine the amount of mechanical energy produced during the motion. So, because the movement is very fast and the flux linkage is constant, so the flux density is constant. Yes, you know that the flux linkage is NBA. Yes, because this is constant, the B is constant. B is constant, Fm is equal to B to the power 2 divided by 2 times mu 0 times the area. B is constant, the force is constant. So we can calculate the force using this equation again by setting the value of the gap equal to 5 millimeter. That is equal to 565 Newton. This is the value of the force. The force during the movement is constant because we considered the constant flux linkage assumption, the constant flux density assumption. Okay, the assumption is very important. How much is the mechanical work done? I am going to calculate it using two methods. The method 1, we know that dWm is force times the distance of movement. In our case, the distance of the movement is 5 millimeters. Yes, the first air gap thickness is 5, the next one is 0. We have a 5 millimeter movement. So 5 times this force is the mechanical energy. This is in millimeter. We have 2.82 joule. Change in the value of the mechanical energy. If we use this equation, dWe equal to dWf plus dWm, because the movement is fast, we don't have a change in the value of the flux linkage. dWe is 0. You know that we discussed it in the first video of this chapter. dWm is equal to negative of dWf, the change in the field energy. How much is the field energy when the air gap is 5? Is this one, B gap to the power 2 divided by 2 times mu 0 times the volume of the air gap. If you replace the numbers, the value of the energy will be equal to 2.82. What is the stored energy in the gap when the gap is equal to 0? The volume is 0 and the energy stored in the air gap is 0. The air gap is closed. So dWf, the change in the value of the energy, field energy, is 0 for the second position minus the energy for the first position, that is negative 2.82. Negative of this right number. 2.82 is 2.82. The change in the value of the mechanical energy. We derived it using two different methods, using this force times distance or this equation. You can practice that. Consider conditions, right? Assumptions. The assumption here is fast movement. The flux linkage is constant. So realize this important point. When we have a fast movement, the value of the force is constant. Okay? So we know that the force is a function of the gap, but this is for the stationary condition. When we set the position of the air gap, okay? When we set the position of the air gap and calculate the force. But in this case, because we have a fast movement, we should consider the dynamic situation, the transient situation. Okay? So this term is important. You can do this simulation. You can do the transient simulation. Okay? And simulate this behavior, but is out of the scope of this video. So just consider this point that when we have fast movement and the flux density remains constant, we have the same force for this structure. That's all. Okay, so yes, it's enough for this video. Let's continue solving the next problems in the next video.